Welcome to our video on martingales, which are stochastic processes that are characterized by the so-called martingale property and are of much importance, in particular in finance. We start by looking at filtrations. So in the last lecture, we have learned that information can be described in form of a sigma algebra. And now in stochastic processes, as we look at the history of a process, so we are looking at information that is gathered over time. We can describe that by non-decreasing sequences of sub-sigma algebras. So we call a collection of sigma algebras filtration if they are nested according to their index set. So for s time s smaller than time t, the sigma algebra at s is contained in the sigma algebra of t. So by stating that, we assume that no information is lost over time. And here we have assumed that our times are non-negative. We can generalize it to general index sets being subsets of R. So in particular, for instance, for whole R, which is relevant in particular for stationary processes. Now, if you look at the right limit of this sequence, so we let t tend to infinity, then the union of these sigma algebras usually is not a sigma algebra, but we can define, of course, then the smallest sigma algebra that contains exactly this union, and we will denote it by f infinity. So if you have a stochastic process X, then we can generate a filtration out of the process. So ft is the smallest sigma algebra that is contained or described by the events of the process X up to time t. So that means if we have any n and any n time points before and up to time t, then these events that the random variables at these time points fall into some intervals. All these events must be in ft, and ft is the smallest sigma algebra containing all these events. We call this filtration that is generated by the process also the natural or the canonical filtration of the process. As a very simple example, a look at repeated coin tossing. So our sample space consists of an infinite sequence of head and tosses, head and tails. So we have an infinite sequence, omega 1, omega 2, etc., where each omega takes either head or tail as a value. Then before we observe any toss, we have no information. And that can be described by the trivial sigma algebra, so the empty set and the sample space. Then after the first toss, we know whether we have observed head or tail in the first toss. So the sigma algebra at that point in time consists of 4 events, namely the empty event, empty set, the full set consisting of the sample space, and then the 2 events consisting of all sequences that start either with head or with tail. Now, already after second tosses, the sigma algebra becomes too complex to write it down or here on the slide. But it's the smallest sigma algebra that consists or contains these 4 events. So all sequences that start with head, 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 tail, tail, head, or tail, tail. Other events that are contained in the sigma algebra are, for instance, head in the second toss. So we have all sequences where omega 2 equals head. So that would be, for instance, the union of those 2 events. Or we can look at the event, same result in the first 2 tosses. So we have all sequences where omega-1 equals omega-2, and that would be the union of these two events. Likewise, we can form a few more other events. Suppose again that we have a probability space, we have a filtration and a stochastic process. Now, if the filtration is not generated by the process, we are usually interested whether or not the history of the stochastic process is contained in the filtration. So whether the process provides additional information or the information provided by the process is contained in the information described by the filtration. So we say that the stochastic process is adapted to the filtration if the random variable xt is ft measurable for all t. So that means that the events that can be described in terms of this random variable are contained in the sigma algebra ft. So if the filtration represents partial information available at time t, the information contained in the sample path of the stochastic process up to time t is assumed to be known at time t if the stochastic process is adapted to the filtration. And of course, it's then clear that every stochastic process is adapted to its natural filtration, so to the filtration generated by the sample path. And that would be actually the smallest filtration to which the stochastic process is adapted. Now we come to our main topic of this lecture. So having again a probability space, a filtration, and a stochastic process, we say that the stochastic process X is called a martingale with respect to the filtration. And we will also see later with respect to the probability measure. If, firstly, the mean of all xt exists, so the expectation of the absolute value of xt is finite, then secondly, the stochastic process X is adapted to the filtration. So the information provided by the stochastic process is contained in the filtration. And finally, so that is the main property, the so-called martingale property, the expectation of xt given the sigma algebra fs, so the information up to time s, equals the value of the stochastic process at time s equals xs. And that holds for all st such that s is smaller or equal t, so s is the earlier point. So that means the expectation of the process at a later point in time given the information up to time s equals the value of the process at time s. 1 and 2 are technical conditions that also guarantee that this, speaking about the martingale property, makes sense. And 3 is, as I already said, the important property that really specifies a martingale. It's called the martingale property. A few examples. So our simplest example is the symmetric random walk. So we have random variables xn that are independent identically distributed and take the values 1 or -1, each with probability a half. Then Fn is the natural filtration of this process. And we generate the symmetric, or we define the symmetric random walk as the sum of the xi up to time n. This is the martingale with respect to the natural filtration. So the technical conditions are easily verified. So firstly, we find that yn in absolute value must be smaller than n, because in each time we can take a step of size 1, either up or down. So after n times, their n steps. So we can go either up or down maximally by amount of n. And then of course, as yn is bounded, its expectation is also bounded. Secondly, yn of course is adapted by this functional definition. So it depends only on the xi up to time n. So naturally, it can be described by these events here contained in the sigma algebra up to time n. So yn is, as a process, is adapted to the filtration Fn. And finally, the martingale property. We can see that yn actually is also a Markov process, can be written as yn minus 1 plus xn, and therefore the condition expectation of yn given fn minus 1 equals yn minus 1 plus the expectation of xn. Now, given the information provided by earlier xn's, however, because the xn's are all IID, we have independence, so we simply have the expectation, and because of symmetry, here we have exactly an expectation of 0, and therefore our conditional expectation is yn minus 1, which establishes the martingale property. Likewise, slightly more general, we can have a mean 0 random walk. So now the xn are independent with mean 0, and yn is defined as y0 plus the sum of the xi. Now we need that the mean of all the xi exists. And then of course we have n such means, the sum of n such means still being finite, assuming of course also if this starting value y0 is random, we also need that has finite expectation. And then of course also yn has finite expectation. And the martingale property is proved in exactly the same way as for the previous example. So it's just a slight variation. So we weaken the assumption by having general distributions. We also don't need the identity distribution. Only we need that the mean of the xn is 0 to guarantee that our conditional mean actually is centered about the previous value. Now, a very interesting general way to generate martingales is the following. So we have a random variable which has whose mean exists. So the expectation of the absolute value of x is finite. We have a filtration, and then we define a stochastic process mt by setting mt equals the conditional expectation of this random variable x given the sigma algebra ft. So which is one of the sigma algebras from the filtration here. And we can easily see that this is a martingale. So firstly, of course, this conditional expectation is FT measurable by the definition of the conditional expectation. And that, of course, means that this process MT, or the process M, is adapted to this filtration. Then the martingale property is a simple consequence of the law of total expectation. So if we take actually 2 time points, so MTFS, so this is not necessarily for discrete time, then we plug in the definition of MT. So MT is the conditional expectation of X given FT. Now we have a nesting of 2 conditional expectations, where the inner conditional expectation is with respect to FT, which contains completely Fs, so the filtration sigma algebra at an earlier point in time. So by that, by the law of total expectation, this is equal to the conditional expectation of X, the original random variable here, given the smaller sigma algebra Fs, which, however, equals Ms. So by that, we have shown that this process satisfies the Markov property. Now, it's interesting to think about whether the converse is also true. I mean, that would be actually rather surprising, but indeed, under mild additional assumptions, so we have a martingale with respect to a filtration, and we additionally assume that the variance is bounded for this process, then there exists actually a random variable M infinity, which also has finite variance, such that our sequence, the stochastic process, converges to M infinity almost surely, as well as in a mean square, which also implies convergence in the mean, so in L1. And we furthermore have that Mn, so the stochastic process at time n, can be described as the conditional mean of this limiting random variable M infinity, given the information at time t, so given the sigma algebra Fn. So that is exactly the converse to the previous result. So there we used it, started with a random variable. Here we call it now M infinity. And we generate the martingale. And we can also vice versa find this random variable X, such that the conditional expectations of this random variable are, again, our stochastic process, provided that we have a few additional assumptions. So here I stated for simplicity this assumption of finite variance. So that means the sequence of variances for the processes, or here the second moments, is bounded for all n, uniformly bounded. There are other forms of this martingale convergence theorem that have slightly weaker assumptions, but we will not concentrate on that. As an example, we look at the so-called Polias urn. So we have an urn that is filled with one white and one black ball. And now in each step, we draw one ball at random and return it with one new ball of the same color. And then we look at the fraction of white balls after the nth draw. So first we rewrite Pn in terms of the previous value. So it is a fraction. So if we multiply, so in the nth step, we have actually n plus 2 balls after the nth step. So after the n minus 1 step, we actually have n plus 1 balls. So if we multiply Pn minus 1 by n plus 1, we get exactly the number of white balls in the urn. So that is the situation before the nth draw. Then a ball is drawn and put back together with a ball of the same color. So we have plus 1 if a white ball was drawn. So if we let xn be the color or denoting 1 if it was a white ball in the nth draw, then we add 1 to the count if xn was 1 and otherwise nothing is added. And then we have to again get the fraction. So we have to divide by n plus 2. Now this shows firstly that we have a Markov process as, oh well, it's not as simple actually, as we would have to show that the xn's here are independent of the past, which they are not, because in distribution the xn's, so the probability by which xn equals 1 definitely depends on the past, but actually it only depends on the past via the actual proportion present in the urn. So the probability that xn equals 1 actually is Pn minus 1. And by that, this is a Markov process, but the argument is a little bit more complicated. It's not just looking at a randomized dynamical system. So next, we want to calculate the expectation. So firstly, we look at the fraction. So the fraction is bounded. So the mean is bounded, the mean exists. Furthermore, of course, we have here a process that is adapted to the information provided by the draws. So, or in any way, it is a martingale with respect to its own filtration. So we are really interested in the martingale property. So we have to look at P n, say, given Fn minus 1. And then, of course, we have simply n plus 1 over n plus 2, Pn minus 1, as Pn minus 1 is known at time n minus 1. And then we have to take the expectation, condition expectation of this indicator function, which actually is simply a conditional probability of the event that xn equals 1 given Fn minus 1, and that divided by n plus 2. Now, I already said the probability that xn equals 1, so that a white ball is drawn in the nth draw, actually depends on the fraction of white balls. So the probability equals the fraction present before the nth draw in the urn, and that is exactly Pn minus 1. So we have here Pn minus 1 divided by n plus 2, and in total we get n plus 2 over n plus 2 Pn minus 1, so which is Pn minus 1, which establishes the Markov property. Now, next, we are interested in the distribution. So we have the probability that we have, say, m plus 1 white balls after n draws. So in order for this to happen, there must have been at m draws. So here we started with 1 white ball. Having m plus 1 balls means that m balls, white balls have been added. So of the nth draws that we have, m were the ones where the white balls were put back, the additional ones, and there are n over m possibilities for that. So to choose m draws for the white balls and the others for the black balls. And then the probability for a particular sequence, we have each time a fraction. So we have, say, if we look at the sequence where we first have the white balls, then we have first 1 over 2. Then we have, if a white ball was drawn, 2 over 3, etc. So in total, if we look at that, we have m factorial over then m plus 1 factorial. And then, of course, we still have to add the draws for the black balls. So then again, we start with 1 black ball out of m plus 1 balls that are present. And then again, the indices are increased. So we have in total, after the draws, n plus 2 balls. We have that factorial. And we have m factorial for the first white balls and then for the black balls. And then we can see that actually the same value we obtain if the white balls and the black balls are chosen in any order, because at each step the denominator increase by 1s, while we, for drawing either a white ball or a black ball, we alternative or take one value, one factor from here or one factor from here, corresponding to whether it's a white or black ball, but we still increase them each time for the next white and the next black ball, and together get still here the m factorial and the n minus m factorial. And now if we put everything together, we get here, after correcting, actually this is 1. As we start with 2 balls before the first draw, so the probability for the first is 1/2. regardless of white or black. And then after n drawn balls, or at the nth drawn ball, we have actually n+1 balls present in the box. So canceling out everything here from the binomial coefficient, we get exactly 1 over n+1. So we get a uniform distribution. Doesn't depend on the number of white balls that are present after the nth draw. The probability is simply 1 over n+1. So, and that means that we have a uniform distribution. So our fraction here so if we now write it like this, so that is exactly m+1 over n+1, as we have added here m+1 such events. And this converges, so this means that if we then look in arbitrary x, that of course would depend on the closest smaller m+1 over n+1, but in the limit tending n to infinity, these steps here will become smaller and smaller, and this exactly converges to x. So we have in the limit for the probabilities here a simply uniform distribution. And this uniformly distributed random variable would be the limiting, so our p infinity. So p infinity in that case is uniformly distributed on the interval 0, 1, the space of all proportions. So we usually very often consider the natural filtration for stochastic process, but the definition is more general, that we can take any filtration, provided of course that our martingale is adapted to this filtration. It is important to note that the martingale property depends on the filtration. And as an example, let's look at the following case. We have two independent standard normally distributed sequences, epsilon and y. And we define x in this form. So it depends, is a linear process. So it depends on the past with this factor yn minus 1 squared plus epsilon n. And we start the process at epsilon 1. So this, given that we know the value for yn minus 1, this is a simple AR1 process. And since we have here yn minus 1 squared, the expectation of y would be 1, and we would have here kind of a random walk behavior, xn equals xn minus 1 plus epsilon n. So we look at two filtrations, the first generated by xm, and as well, the x's, well, they're constructed out of the y's and the epsilons, but we cannot easily generate the y's and the epsilons out of these x's. So our other filtration consists of the information provided by the stochastic process x and y. So if we then look at the martingale properties, so firstly, the condition expectation of xn given the information in f up to the previous point in time, then since yn minus 1, so here we multiply by yn minus 1, we can actually see that because the previous x's here only depend on the y's to the previous point in time, and the epsilons are independent. So actually this particular value here is first included in the xn, so it's independent of the complete path of the process. And by that, it is clear that we simply have here the second moment of this random variable. And because we have a standard normally distributed sequence, this is simply 1. So we have indeed here this martingale property. Our xn behaves like a random walk, at least on average. Now, vice versa, or in contrast, if we know ym, then of course our conditional expectation here is simply yn minus 1 squared times xn minus 1, and then it would depend on the realization, which almost surely, of course, is not equal to 1. So the martingale property is almost surely broken. So our process x is a martingale with respect to the smaller sigma algebra, but not to the bigger one. Now a few properties about martingales. The first becomes available after repeating the martingale property repeatedly, at least in discrete time. The general martingale property anyway looked at 2 different points in time. And if we think about x0 as the starting value, so that would be simply provided information or no information at all, so the trivial sigma algebra, then the expectation of xt given this trivial sigma algebra equals expectation of x0 at the trivial sigma algebra. So this is a straightforward consequence of the martingale property, which means the mean does not change over time for a martingale. That is a necessary condition, but not sufficient. So we can have plenty of processes that have a mean that are constant over time. For instance, every stationary process must have a mean that is constant over time, but they are not in any means martingales. So the martingale property is a much stronger statement, and it does not simply consist of the mean being constant over time. However, whenever this is violated, of course, we cannot have a martingale. About the interpretation of martingales, so what are martingales? We often use them as models for fair games. So suppose you play at the times of the index set. So you can have games at discrete points in times or continuously over time. And the stochastic process of interest describes your wealth at these times. So after having played, then our best prediction of the future winnings would be, so the winnings are how your wealth changes. Your prediction would be conditional on the information you have at time s. Then it would be the conditional expectation of xt given fs minus xs, which is known at time s. So how this conditional expectation differs from the current value of the process. And the martingale property implies that this equals 0. So that means your prediction of future winnings is 0. And that exactly would be fair because neither side makes on average a gain. Now, fair games are seldomly found. So in a casino, for instance, the games are biased against the player. And in that case, we speak of a super martingale. So where the mean of xt given the information up to previous point s is smaller or equal xs. So the interpretation with respect to wealth, you expect your wealth to be smaller than your current wealth. That is the situation you should have in the casino. We call it a super martingale and a sub martingale if the expectation is larger or equal your current state. So a super martingale would be disadvantageous for a player, while a sub martingale is favorable. One way we can easily construct sub or super martingales from a martingale is by means of the Jensen's inequality. So suppose we have a filtration and a martingale with respect to the filtration and a convex real-valued function, and we apply that function to this martingale. We assume theoretically also that the mean of the absolute value of the convex function of mt exists. So in order to classify phi mt as a sub or super martingale, you of course need to establish the theoretical properties. In particular, the mean must exist. And then we can define the process xt, which now has finite mean, as the evaluation of the function phi at the martingale mt. And this is a submartingale with respect to the filtration. And this is simply a consequence of Jensen's inequality. So we have the condition mean of xt given, say, fs. So that is the mean of condition mean of phi mt given fs. By Jensen's inequality, this is a larger or equal the convex function evaluated at the conditional mean, which now again is xs. And this establishes exactly here in total the submartingale property. Likewise, if we have a concave function, then this inequality reverses and we have a super martingale. As an example, for instance, if we have a martingale and we put it into an exponential function, which is a convex function, then this process xt is a submartingale. Now, to wrap up today's lecture, we have a few more slides on minor topics. So first is looking at so-called martingale difference sequences. So we have a filtration and a martingale with respect to the filtration, and we look at the first difference of this process. So delta Mn equals Mn minus Mn minus 1. Then the mean of this first difference process, simply the conditional means are simply 0. Such a sequence is called a martingale difference sequence because we take the first difference of the martingale. Now, martingale difference sequences are of importance, especially in time series analysis, as a generalization of so-called white noise processes. So if we have models like the autoaggressive or autoaggressive moving average process, the innovations, the noise process is usually considered as a zero mean independent process or white noise process. And this assumption of independence or uncorrelatedness can be weakened to allow for some dependence, namely those that can be described by martingales, or our noise process is a difference process, and by that has a mean 0. So we still have a mean 0, no systematic error coming into the system, but that shows some dependence, namely that is still in this martingale difference through the martingale process. So it should be noted, as martingales only look at the mean, the martingale property only looks at the mean and restricts the mean of future points, the conditional means, to be the current value. That leaves open a lot of dependencies in the higher moments. And that is exactly what can be exploited here, that we, for instance, can have a lot of dependence in the higher moments. And using these martingale difference sequences as a substitute for white noise processes or for IID sequences, in particular for IID sequences, we then also need similar results, namely, for instance, central limit theorems. So we have here, for instance, just cited, we will not use it in this course, a theorem that establishes central limit theorem. So asymptotic normality for some of such innovations. So we have a martingale difference sequence, or actually an array, where in each row we have a martingale difference sequence, but these are allowed to change with an increasing index. So they form a triangular array. And we make certain assumptions. They are actually similar to the assumptions needed for the more general forms of the central limit theorem. So this establishes that the mean or the variance of our process here equals the limiting variance of the limiting normal distribution, standard normal distribution. And we get then, as in the central limit theorem, an asymptotic standard normal distribution. But we have not assumed here independent identically random variables, but martingale difference sequence, which is considerably weaker. Now, finally, we also look at martingale transforms. These martingale transforms are discrete analogs to the stochastic integrals that we will look into at the end of this course. So again, we have a filtration, we have a martingale with respect to the filtration, and additionally, we have an adapted process that is also adapted to the filtration. Then a martingale transform, denoted as, say, x equals phi dot m is simply taking the martingale difference sequence obtained from the martingale m and multiplied for each time I by our adapted process at the earlier point in time. So this is a difference in the martingale sequence from time I minus 1 to I. And this value here, by which this increment is weighted, is actually known at the beginning of the, or at the left endpoint of the interval over which this increment is taken. That is a very important concept. And with that, such martingale transforms could, for instance, be easily seen as investment strategies or also gambling rules. So namely, if we play games and our winnings in the game would be according to this martingale here, or the martingale difference, then we of course can bet certain amounts, and this phi here, phi I minus 1 at the left endpoint of this interval, actually defines the amount that we invest or the amount that we bet, and then the product here will reflect our gains over this period. And of course, we can only use information that we have available at the left endpoint at the beginning of the investment period. So this must be known at the left endpoint. So this must be firstly adapted to the filtration. We use the information that we have available. And here I make it by this using I minus 1, simply visible that this random variable is known at the left endpoint. In the literature, sometimes you find phi I here used, so in correspondence to the I that we have here, but then one must make the assumption of previsibility so that this point actually still, this random variable phi I is actually known at time I minus 1. So one can escape this notion of previsibility by simply stating the right endpoint. So the correct endpoint, namely the left one. Then interestingly, these processes provided this adapted process phi is bounded, actually forms again a martingale, which has a very interesting interpretation, namely if you have a fair game described by this martingale M, or you have a fair investment described by this martingale M, then there is no strategy that you can run, no feasible strategy that you can run that makes you win after in a finite amount of time, that makes you win consistently against the underlying martingale. So you still have a fair game, so your expected losses or gains are still 0. You cannot beat the martingales here, the underlying martingales. So there, in a gaming, there's no gaming strategy, feasible gaming strategy, by which you can consistently make money out of these games. So, as I said, this delta Mn is a martingale difference sequence, so its expectation is, condition expectation is 0, and therefore we can describe the condition expectation of xn plus 1 given the earlier point in time simply as xn plus phi n is known. So we have here phi n times delta m n plus 1. It is known, so by stability law, we can pull the phi out of the condition expectation as we condition on information available at time n. And then we have here the condition expectation, which is 0. Therefore, this additional term cancels out and we simply have xn. So this process is a martingale. The boundedness of the phi n we need to ensure that actually this process x has actually finite mean. Now, often it's also interesting to have the converse results. So you have two martingales with respect to the same underlying filtration. Can we then also write the one as a transform of the other? And that is in general not the case, but in special cases, two important special cases, it's actually true. And the one we can here easily describe is our so-called binomial tree. So we have binomial random variables or Bernoulli random variables, Zn, and a random walk that is constructed out of these. So we simply look at the number of successes in n trials and get by that a random walk xn with natural filtration fn. And now we have two martingales with respect to the same filtration. So that means that if we describe this process as a tree, so each time we have two possibilities. So we have success or failure, success or failure, success or failures, and the number of successes are the values in the nodes. So the tree reconnects here. We have one failure, whether it's the first or the second trial, doesn't matter. So that is our tree. And having now two martingales with respect to the same filtration means that these martingales also move together with the underlying xn process on this tree. So at time 1, if the process goes up, then also mn and nn take together the value they have in this situation. So these things move together. And in that binomial case, we can then easily see that there exists a process that is also bounded. The boundedness anyway here is obvious as our m's and n's in this binomial process are bounded, and therefore such an equality also implies that the phi must be bounded. So we have a bounded adapted process such that we can express the one process as a martingale transform of the other. So that works, of course, both ways. Or equivalently, we can write the change in the one process equals a factor times the change of the other factor. And this factor actually is known at the beginning of this time period. So it's fn minus 1 measurable using the information up to time n minus 1. We know this value. So that has, again, important consequences. So that is used, for instance, in finance, if we have two assets that can both, like for instance, a stock price and a so-called financial derivative whose payment completely relies on the underlying stock. So it moves together with the stock on a binomial tree. If you use a binomial tree as a model for the stock price, we have already seen that. So by going up and down by certain factors. So such a process would be also adapted to the filtration of such a binomial tree model, as we simply look at the number of successes, the number of upturns. And as the financial derivative and the stock price move together on the tree, if you then can describe their price process by martingales, which under certain circumstances we can do, then we find that actually we can connect these price process in this form. So that means we can write the one price process by a trading strategy using the other asset, which has important consequences, namely, we actually wouldn't need financial derivatives because we can completely synthetically create them by trading only in the underlying stock. And that has, for determining the price of such a financial derivative, very important implications. Basically, it guarantees that we can find the price, the fair price, by this replicating trading strategy. This completes today's lecture on martingales. In the third part of this week, we will have a look at stopping times and theorems that deal how the Markov property extends to stopping times. Thank you for your attention.